Now we're going to look at this thing called demoivres theorem. Here is demoivres theorem. It's actually something you already know, but it's just been formalised. Because if you look at it, all it's really saying is, if you have z to the power of n, the argument of that is n theta. That's really all that's saying. Because we're saying cos theta plus I sine theta to the power of n becomes cos n theta plus I sine n theta. So we multiply the argument by n. Notice the modulus of this is 1. So of course we could extend that to cater for all complex numbers by simply putting the modulus r out the front, and then in the answer it becomes r to the power of n. I mean, that's all we need to do. So if we want to find 1 minus I to the power of 5, I mean, yes, we could expand the whole thing out. But this particular one's not too bad because, well, we know the modulus is root 2. The argument becomes minus pi on 4. So we can say, well, okay, if I change that into mod arg form, I get root 2 cis minus pi on 4 to the power of 5. So using demoivres, we can say, well, the modulus I'll raise to the power of 5, but the argument I'll multiply by 5. Root 2 to the power of 5 would be 4 root 2, I think. Yeah, 4 root 2. And, well, there it is in mod arg form. Minus 5 pi on 4. Remember, we like to put our arguments between pi and minus pi. So minus 5 pi on 4 will be the same as 3 pi on 4. But if I wanted to know what it is in Cartesian coordinates, then all I've got to do is work out the cosine of 3 pi on 4, second quadrants. So the cosine's negative. Acute angle's pi on 4, so that's 1 on root 2. So we'll have minus 1 on root 2 plus 1 on root 2, expand out, and there's our answer, minus 4 plus 4i. I mean, is that quicker than just expanding out 1 minus I to the power of 5? Meh. Maybe it's the same sort of working up, but I guess you can appreciate as that power gets higher and higher and higher, then this theorem becomes more useful. Because the higher the power, obviously there's a bigger expansion you would end up having. Now just a note on this, if it's said, put your answer in mod arg form, so like I have over here on the left, 4 root 2 cis 3 pi on 4, then that's the answer I would put. I would not put minus 5 pi on 4, because again, remember, we said we want our arguments between pi and minus pi. But if it had said do it in Cartesian, then I'm probably not going to bother changing that to 3 pi on 4, because the cosine of minus 5 pi on 4 is the same as the cosine of 3 pi on 4. So there's no real need to convert it if eventually I'm just going to the minus 4 plus 4i. Up to you, of course. I mean, you can still convert it if you want to. Well, this now allows us another way of finding roots, right? Because if we now know z to the power of n is x plus iy, and we want to know what z is, so we want to find the nth root. If I change that to mod arg form, so r cis theta, then the modulus I'll find the nth root of, but now the argument I will divide by n, because we're going back the other way this time. Instead of finding the power, we're finding the root. But notice I've added in this 2 pi k on top, because when it comes to roots, we'll have the same number of roots as whatever the power is. So when you find the square root in complex numbers, we get 2 answers. Cube root, we get 3 answers, and so on. So this will generate all the solutions. And so k will equal 0, 1, and so on, up to however many we need to get the solutions that we want. Now, a little trick here, we don't have to substitute in 0, 1, and so on. We're just substituting in consecutive numbers. So if you know the solutions are going to be in conjugate pairs, so in other words, the coefficients of your original equation are all real, then it's a little bit more efficient to use plus or minus, because that'll get the conjugates straight away. Show you what I mean. Well, this one it won't work for, because z squared is 4i, and that's not real. So I will do it this way. I change 4i, well, that's 4 cis pi on 2, of course, because it's purely imaginary, so it's on the y-axis, we know that. So z will be 2 cis pi on 2, plus 2 pi k, over 2, and I want to generate 2 solutions, so I'll say, well, k equals 0 and 1. Substitute in 0, and we get 2 cis pi on 4. Substitute in 1, we get 2 cis 5 pi on 4. If I was going to put this in mod arg form, then I would change the 5 pi on 4. But in this case, I'm more interested in the actual answer in Cartesian form, so I'm not going to worry about it. So the cos of pi on 4, 1 on root 2. Sine's also 1 on root 2. 5 pi on 4 is in the third quadrant. So cosine and sine are both negative. And there's our answer, root 2 plus root 2i and minus root 2 minus root 2i. Another way I could do this, yet another way of finding them. I really only need to find one solution. Okay? So there's my first solution. There's that 2 cis pi on 4 that I would have got. If I didn't worry about that 2 pi on k, I would have got, okay, 2 cis pi on 4. If I remember that the solutions are going to be symmetric. So if there are two solutions to this, then the next solution must be 180 degrees away, or pi radians. Okay, so 2 pi divided by 2 for two solutions. So therefore, I know the other solution is 2 cis minus 3 pi on 4. So I could do it visually and come up with these two answers. All right, here's one where we're dealing with real numbers, so I can use the conjugate idea. I know the solution to this will be in conjugate pairs. So we're saying x to the power of 4 is 16. Well, 16 is the same as 16 cis 0. So it'll be 2 cis, 2 pi k on 4. K will equal. So I'll start with 0, but then I go plus or minus 1. And then the next one will be 2. I mean, I could have done negative 2. It doesn't really matter which one I pick, because I'm just looking for, in this case, 4 consecutive numbers. So that gives me 2 cis 0, 2 cis pi on 2, 2 cis minus pi on 2, and 2 cis pi. And they're all nice and easy ones to find out, because they're all on either the x or the y axis. So we've got 2, 2i, minus 2i, and minus 2. Now, if I did that visually, I could say, well, the 4th root of 16, I know that's 2. So there's my first solution, 2. But there's going to be 4 solutions in the circle. So therefore, they must be 90 degrees or pi on 2 radians apart. So the next one will be there, but then I know its conjugate will be there. And then the next one must be over on the negative side of the x-axis. So there's my 4 solutions. So let's find the 4 roots of 1 plus root 3i. So it's not real, so in this case I'm not going to use the conjugate idea. So z to the power of 4 is 1 plus root 3i. 1 plus root 3i is 2 cis pi on 3. 2 cis pi on 3. So I'll get 2 cis pi on 3 plus 2 pi k over 4. I want the 4 consecutive solutions. They're not conjugate pairs this time, so I'll just go 0, 1, 2, 3. And there's my answers. Cis pi on 12, yeah. Oh yes, 4th root of 2, where the modulus was 2. I did a bit of cut and paste. So yes, the 4th root of 2, cis pi on 12, cis 7 pi on 12, cis 13 pi on 12, and 19 pi on 12. If we're going to leave it in mod arg form, which I am, because I don't know the exact value of cos pi on 12 without, well, we could work it out. So I'll leave it like that, which means the 13 pi on 12 will become minus 11 pi on 12. And the 19 pi on 12 will become minus 5 pi on 12. Again, if I did that visually, there's my first solution. I've got 4 solutions, so every 90 degrees. So there's my next one, it's 7 pi on 12, then minus 11 pi on 12, and minus 5 pi on 12. So whether you do it visually, or whether you do it algebraically, it's your choice really. Notice they all lie in a circle, isn't that nice? Hey, there we go. So exercise 3A we'll have a go at.